Okay, thanks a lot for the introduction, Paul. As already mentioned, my title is Deleterious Minerals in Concrete Aggregates, the Swiss Experience. And I would like to acknowledge my co-workers. Back, please. Oh, no, that's the wrong. Two, one, please. Not three, one, please. Well, I would like to acknowledge my co-workers Beat Münch and Barbara Luttenbach. So the outline of my presentation: first, I will give some personal information, then I shortly talk about the dynamics of research and standards in Switzerland. I show which standards we apply on aggregates, and then I will talk about the Swiss experience with the deleterious minerals, first mica, and then somewhat longer about pyrrhotite and internal sulfate attack. I will show the chemical reactions taking place, and I will present some preliminary results from concrete blocks northwest Donegal, Ireland, that I have received from Paul Dunlop, and I will draw preliminary conclusions. And I have to mention that my work so far has been only motivated by scientific curiosity. So I will end with a summary. Next, please. So personal information: I have a master in geology and did a PhD in liminal geology. Since '95, I'm at Empa. I'm heading the concrete technology group. I'm a member of several national, international committees and standardization groups. The research topics I work on, the main focus is concrete durability, and this includes a lot of microstructural analysis. But I work as well with recycling concrete and special concrete mix designs. Next, please. So, dynamics, research, and standards. Several Swiss concrete standards and their limit values are based on results of research projects. This goes from freeze-thaw resistance to chloride resistance, sulfate attack, carbonation resistance, and water conductivity. The impact my research had on standard was the following. The research on mica resulted in adaptation of the Swiss standards on concrete aggregates. My work on external sulfate attack led to the redesign of the accelerated test in the Swiss standards, and an alternative method to test sulfate attack was rejected based on a project I did. So you see, research can really influence standards. Next, please. So what are we using for concrete aggregate standard-wise? So we have a Swiss standard, 670 115. It limits the amount of deleterious minerals in the aggregates to 5 mass%, and this includes mica. If the amount is between 5 to 10 mass%, concrete tests have to be performed to show that the concrete reaches defined performance criteria. Now, about iron sulfates. Swiss standard SN EN 12620. There are limits given there to total sulfur content of the aggregates, and how this sulfur content is determined is defined in another standard, the SN EN 1744.1. And if you look at the table at the bottom, you see there the total sulfur content. There are in principle 3 categories. If your total sulfur content is below 1, so it's S1. If it's above, it has to be declared, and there's a class with no requirement. And it is stated that special precautions are necessary if pyrrhotite is present in the aggregate. If this mineral is known to be present, the maximum total sulfur content of 1% as sulfur shall apply. Next, please. So what is our experience with mica in the aggregates? So it was a major issue during the construction of the Gutter Tunnel built between 1999 and 2016. It's the 57-kilometer long tunnel crossing the Alps. It was defined excavated rocks had to be reused as concrete aggregates. And the mica content in general was high, sometimes very high. What did we learn from this? A high mica content increases water demand to reach a certain workability in concrete production. If you counteract this with adding more water, which means increasing water-cement ratio, this results in a decreased concrete strength, increased water absorption, and so on, which just means decreased quality. If it is counteracted by increasing cement and superplasticizer content and unchanged water-cement ratio, relatively small impact is observed, and this is shown by a lot of strength and durability tests. The biggest challenge during the project was the continuous adaptation of concrete mix design to changes in aggregate quality, and this included content and type of mica and layer silicates. So we had all type of mica and layer silicates possible, more or less. Just no clays, I have to mention this. In one section that was a few kilometers long, mica content was decreased using a special flotation technique. And what our experience has clearly shown, presence of mica in hardened concrete does not lead to deterioration like by humidity changes. The mica we have in Switzerland show no swelling at all. Okay. Now, please to the next slide. So our experience with pyrrhotite or iron sulfate oxidation in general that is linked to internal sulfate attack. So we had only actually one major case in Switzerland, and that's the Isolo Dam built between 1957 and 63. It's a gravity dam, 290 meters long, 45 meters high. It started to expand continuously in the mid-80s, and due to this swelling, operation was impaired. So last year, the dam was cut. So on image A, you see a top view of the dam. Image B shows an installation of the cutting equipment. And in C, you see what has actually been done. Well, first, of course, the water had to be released before this was done. You drill a hole through the entire dam, more than 6 meters wide. Then you insert a wire saw and cut the entire cross-section of the dam. So about 10 tons of concrete were removed that way, and the gap was filled with a soft watertight material, and the stress was released, and the dam is back to operation. Now, what does actually happen in this internal sulfate attack? And that's what I want to talk now. Please, next slide. So don't be afraid, it's not as complicated as it looks like. So what do we have here? This is an image that was done with thermodynamic modeling. Now, what you have are the hydrates formed by cement hydration. So this is what is present in your concrete. Now let's start to the left-hand side. At the bottom, I just highlighted the phases that are important to explain what happens. So first, you have the calcium silicate hydrate, abbreviated CSH. You have ettringite, you have monosulfate. Now, you put pyrrhotite on top of it. And going from the left to the right, you oxidize this pyrrhotite. This means sulfur is released into the concrete. And now please look at the green area represented by the monosulfate. When you release sulfur, the amount of monosulfate gets smaller and smaller until you reach the dashed line, okay? Ettringite is formed on the expense of monosulfate. And if you form ettringite in a hardened concrete, you will experience stress, expansion, and cracking. But it doesn't end there, because still more sulfur is released. And when all the monosulfate is used up, you start with phase 2. A new mineral is formed. To the upper right, you see thomsite. Thomsite is a very soft mineral. You can smear it between your fingers. And thomsite forms on the expense of calcium silicate hydrate, the CSH. And CSH is the phase or the hydrate that gives the concrete its strength. So the second phase is connected to a strength loss of your concrete. In extreme cases, the iron oxidation products may add to this expansion, but the main issue here is the minerals that form by the sulfur release. Now, how does this look like in reality? And for that, I would like to jump to the samples I got from Paul Dunlop, 4 samples in total. Next slide, please. You see this very nice mineral here. This is thomsite, and look at the scale at the bottom, so 5 micrometers. Thomsite needle is probably about 1 micrometer across, so a human hair is about 60 micrometers. So you see this is a really fine needle. Okay, now this image was done with a scanning electron microscope, and now let's move one further. Next, please. Okay, this is a polished concrete section. You see the scale as well. The grayscale values, they more or less represent the density of the phases you have here. Standing out, very bright, this is pyrrhotite. What you can observe as well in this bright mineral are veins that are somewhat darker. This is oxidized pyrrhotite. To your left-hand side is more or less the cement paste. Now, I did a sulfur mapping of this, showing where the sulfur at this particular location is. Next, please. Okay, the brighter the blue, the more sulfur is here. Okay, so you see, of course, pyrrhotite stands out. However, you see these bluish pockets in the cement paste. And now you can perform more element maps, sorry, can perform more element maps and form a so-called phase map. Next, please. Now, the legend is in your lower right corner. Dark green is the aggregate, bright orange the pyrrhotite, then yellow is the CSH that gives the concrete its strength. Green is ettringite. And very important here, you don't see monosulfate anymore because all the monosulfate has already been transferred to ettringite. This means this concrete has already gone through an expansion phase. And more than that, you see the pink mineral, this is thomsite. So CSH is already transformed into thomsite, which is connected to a strength loss. Next, please. So this is another sample. Looks pretty harmless, whatever. But let's do a sulfur mapping. Next, please. You see you have these two bright spots. These are two small pyrrhotite particles. And then you have a relatively homogeneous area of pink, which means homogeneous sulfur distribution. Now we do the same thing again as before. We produce a phase map. Next, please. Legend upper left corner, dark green aggregate, orange pyrrhotite, yellow CSH, green ettringite, and now you see this large pink area. This is thomsite. This concrete has gone through a severe strength loss. And unfortunately, the story doesn't end here. You have a natural process that concrete is exposed to. It's called carbonation. This means concrete reacts with CO2 from the air and forms new phases. Usually, this is harmless. However, if you have a concrete that has gone through phases 1 and 2, which means internal sulfate attack, it's not that harmless. Next, please. Again, I use thermodynamic modeling to show what happens. On your left-hand side, you see the minerals that are present after phases 1 and 2, and highlighted the thomsite. Now from the left to the right, you add CO2, which means you carbonate the concrete. And look what happens to the area that is blue and representing thomsite. You see that the carbonation boosts thomsite formation, which means more strength loss. When your concrete is completely carbonated, at the very right side, you have some phases at the top, mainly silica gel, then you have gypsum, and then you have calcite. And gypsum is the only phase that is kind of a witness that shows what has happened before the phases 1 and 2. And I have to stress, gypsum does not form directly in phases 1 and 2 because the pH is just too high. It forms at the end. And gypsum is water soluble, which means when your concrete is getting wet, it disappears. Next, please. Back to the concrete. This is a section of cement paste. Again, we do the sulfur mapping. Next, please. Now you see only 3 spots that have this blue color, which means where the sulfur is. Again, a phase map is done. Next, please. So again, dark green the aggregate, yellow the calcite, pink the silica gel, both products of carbonation, and green the gypsum, the only witness that is left from what has happened before. Next, please. So the Irish concrete blocks, preliminary conclusions from a limited number of samples. Deterioration of the analyzed concrete blocks is not a mica problem. The analyzed concrete blocks suffer from internal sulfate attack triggered by pyrrhotite oxidation with sulfur release followed by carbonation. Phase 1, formation of additional ettringite leads to expansion cracking. Phase 2, formation of thomsite leads to strength increase. Phase 3, carbonation boosts thomsite formation and at the end leads to formation of calcite, silica gel, and water-soluble gypsum. The extent of phases 1 to 3 depends on the amount of pyrrhotite oxidation, and with that, of course, the amount of released sulfur, concrete quality, and exposure, which means humidity. Humidity accelerates the reaction. And the results should be backed up by further analysis of concrete samples. Next and last slide, please. So the summary. Scientific findings can influence standards or even be the base of them. Mica and other layer silicates. The impact of mica can be counteracted by adaptation of concrete mix design. Mica does not lead to deterioration of hardened concrete. Amount allowed can be regulated by the standards. Now to pyrrhotite or iron sulfate oxidation and internal sulfate attack. Pyrrhotite in aggregates can have disastrous effects on concrete. The amount allowed can be regulated by standards, but I have to admit as well that performance-based tests may allow more precise assessment of aggregates with pyrrhotite than chemical tests, and I think Benoît Fournier will talk about this. Thank you for your attention.
Thanks very much, Andreas, for that really interesting talk. And you made the science, I think, accessible to people back home listening, and also to the all our delegates. And maybe if people have questions, they can type them up in the box, and we can maybe have a chance to look at those later. So some very interesting conclusions from preliminary work from a small number of samples that we've taken back home in Donegal, but it does show you that that the pyrrhotite is a major problem actually in Donegal too, and it has been overlooked so far in the standards. So I think it's something that needs to be looked at by NSAI for changing.